So in this video, we'll take a look at how we can use Fermat's theorem in order to tell us something about whether a number is prime or not. And to be specific here, as we'll see, it doesn't actually tell us that a number is prime, but it can tell us that a number is not, right? In other words, a number is composite. And well, how can we see that? So for Fermat's theorem, the statement is as follows. If A is a natural number and P is prime, such that, well, they're co-prime or relatively prime, then this congruence holds, right? So that's the conclusion there. In other words, if we have a natural number A and a natural number M, such that they're co-prime, and if that congruence up there did not hold, so A raised to M minus 1 is not congruent to 1 mod M, then we can conclude here that M is not prime. Right, so you see what's happening here. This is what we basically negated, right? You can think of that as the contrapositive of Fermat's theorem. When these two assumptions hold, that A is a natural number and they're co-prime, that the conclusion of Fermat's theorem doesn't hold tells you that P couldn't have been prime in the first place. Or that's why we're using M here, right? To just talk about the general scenario. And so this is nice, right? This means I only have to compute this thing, right? Or check it. And if I get a remainder that's not 1, when I divide A raised to M minus 1 by M, then immediately I can say, well, therefore M can't be prime. Okay, I'll give you an example. Let's show that 91 is not prime. Right, and we all know 91 isn't prime. It's 7 times 13. But how can we actually use Fermat's theorem to do that? So Fermat's theorem says if 91 were prime, then 2 to the 90 must be equivalent to 1. So let's prove that it's not. And if it's not, it can't be prime. So how do we compute this remainder? Well, here's the catch. You can't use Euler's theorem nor Fermat's theorem to do this, right? Because we're kind of assuming here that we don't know whether 91 is prime or not. And the use of Fermat's theorem and Euler's theorem, right, assumes that we know that, right? We need phi of 91 for that. And knowing that tells us whether it's prime or not. And so let's just keep multiplying 2 by itself and see the pattern here. 2 squared is 4. Let's keep squaring, I guess. 2 to the 4th power is 16. 2 raised to the 8th power, which is that squared, is 256. And this is now congruent to 74 modulo 91. And you basically just have to keep going here until you notice some pattern. In fact, you'll see that if you keep going to 2 to the 12th power, right, if you somehow multiply 2 to the 8th and then you multiply 4 more copies of 2, you will actually get something that is congruent to just 1 modulo 9 to 1. Right? And so, okay, so we can use this, right? Therefore, 2 to the 90 is congruent to, well, first of all, it's equal to 2 to the 12 raised to the 7th power times 2 to the 6th. Right? That's 84 plus 6 is 90. And that's congruent to 1. And what's 2 to the 6th power? It's 64. Right? And therefore, this tells me, therefore, since 2 to the 90 is congruent to 64 modulo 91, 91 is not prime. All right, because again, if it were prime, then we would have gotten just 1 here as a result. Okay, so let's look at another example. Can we conclude that 91 is prime by picking A to be 3? Right, because remember this. If 91 were prime, then for any integer a from 1 to 90, then a to the 90 would be congruent to 1 modulo 91. Right? Because if it were prime, then all the integers here would be relatively prime with 91. So on the previous slide, we showed it for 2, that it's not 1, and that would be enough to conclude it's composite. Let's look at it for 3. What's 3 to the 90 mod 91? Well, okay, well 3 cubed is actually 81, right? And that's negative 10, so maybe that helps us a bit here. Let's see. Oh, and I multiply by 3 one more time, and that's congruent to negative 30. So let's make this 3 to the 5th power. If we actually multiply this by 9, you get negative 90 mod 91. What's negative 90 mod 91? It's 1 mod 91, right? Just add 91 to it, and you get something else that's congruent. And it turns out to be 1. Therefore, 3 to the 90 is actually, well, since it can be written as 3 to the 5th power raised to 18, therefore 3 to the 90 is congruent to 1 to the 18th, or just 1 modulo 91. And you might be thinking now, right? Well, does this prove that 91 is prime? Well, clearly not, right? Because it isn't, right? But if you look at the result here, it does look like the conclusion of Fermat's theorem holds for a equals 3 and m equals 91. Right? But remember what we said here in this slide. We said that the implication went this way. If p is prime, then the congruence holds. Which means to say, going the other direction does not necessarily follow. Right? So if this congruence is true, it's just inconclusive. Right? Doesn't actually tell us that it's prime. If it's not true, then sure, you can say it's composite. Right? But in this case, as we see here, you can get into situations where it is a true statement, that it is congruent to 1, but, well, you can't conclude that it's prime just from that statement.